Hi, welcome to this video. I'm Athanaeus, and in this video, I will show you how to use the Vibration Educational Training System, or VETS for short. This system was developed for educational purposes, and this video is meant to guide future students who wish to continue developing and improving the system. Let's start by looking at the complete setup. The system consists of a power amplifier, NI data acquisition system, vibration shaker, custom-made stinger, 3D printed card, slotted mesh, function generator, and an accelerometer. First, let's power on the system. Begin by turning on the power amplifier. You can adjust the current level toggle, which control how much current goes into the shaker, and the variation gain toggle, which control the signal strength. Next, switch on the function generator. Press the power button, select a sinusoidal wave, and set the frequency range to 10. Then, turn the frequency adjustment knob slowly. This will change the frequency of the signal sent to the shaker. For this experiment, you need to slowly sweep through different frequencies to find the resonance of the system, where the vibration is the strongest. As you turn the knob, you will notice the shaker begins to move. We use a sinusoidal wave because it is smooth and helps us clearly see how the system responds at different frequencies. The frequency range is set to 10, so we can focus on lower frequencies that are suitable for this small-scale vibration setup. Important note, do not start the system with a high frequency or suddenly increase it too much, as this could damage the shaker. Now, let's assemble the 1DOF setup. Use one card and connect it to a spring using the spring mount. Then, connect the other end of the spring to the stinger. Make sure all nuts and bolts are tight, as loose connection can cause noise in your result. Next, take the accelerometer, plug in the cable, and mount the accelerometer on the 3D printed card. There is an arrow on the sensor. Make sure it points in the same direction as the card moves. Connect all the other end of the cable to the NI DAQ system, in this case to port AI0, and then connect the DAQ system to your laptop. Now, open FlexLogger software, create a new project, find channel AIO and rename it as MES1. Set the physical measurement to acceleration, sensor class to IEPE, and the unit to meter per second square. Set the sensitivity value based on the label found in the accelerometer manual, which should be included in the casing. Then go to the Screen tab to create your user interface. Drag the frequency spectrum graph and the long history graph into the canvas. Adjust the graph values to suit your data. When ready, press the green Run button. Now the system will start logging acceleration data. At this point, power up the shaker and begin your frequency sweep. You will see a peak on the graph when the system reaches its resonant frequencies. Now, let's move on to the 2DOF configuration. Add another card and set it up the same way as the first card. For the second measurement, use a triaxial accelerometer. Choose one direction. Here we use the Z direction. Make sure the Z direction is aligned with the direction the cards are moving. In FlexLogger, assign the channel just like before and set the correct sensitivity value from the manual. Now your 2DOF system is ready for testing. When the experiment is done, press the red stop button to end data logging and export the data as a CSV file. Open MATLAB, click the Import Data button and select the file you just exported. The file will show up on the right side. You can write your own MATLAB script or use mine. In my example, I type in the file name, run the script, and the data is analyzed and displayed in a graph and in the command window. After finishing your experiment, continue your analysis by doing manual calculations and using SolidWorks to simulate the model. Then, compare your experimental result with your theoretical and simulation result. Before I end this video, I'd like to share some suggestions for future students who want to take this project further. First, try adding more degree of freedom to study more complex vibration system. Second, consider redesigning the card to be more durable and easier to maintain. Lastly, explore using this setup for acoustic or more advanced dynamic testing. That is all for this demonstration. Thank you for watching, and I hope this helped you with your project.